So hello, welcome student for today's class. So this is MA425 Topology, and today we have lecture number 17. Okay, and so let us discuss some properties of connected space, whatever we were discussing last day. And recall that we proved that if you have a connected subspace of a set, then the closure is also connected. Okay. In fact, if you add some limit points of this connected space, it doesn't matter; it will again become connected. Okay. So now we will start with another very important property, and that is called that the continuous image of connected space is connected. So let me start with that theorem. Okay, and this theorem tells you that continuous image of connected space is connected. Okay, so what does that mean? That means you have a connected space, and if you have image under a continuous map, then the image will be also connected. Okay. Okay, and then how do you prove this thing? So proof. So suppose so you have that space. So let X be a connected space. Okay, and the continuous image. So suppose you have continuous functions. If from doesn't matter anything, say y is continuous. Okay, so what is our claim? Our claim is that f of y, x is subspace of y, right? So this is connected. In particular, if we start with the surjective map, then we need to prove y is connected. Okay, so it doesn't matter. Obviously, the map from x to f of x is surjective, right? So how to prove? So we use the mathematical contradiction of mathematics. Okay, so on the contrary, let us assume that fx has a separation. Okay, something say uv. Okay, then obviously you know that f of x can be written as u union v, where both u and v are open in fx, right? And obviously they are disjoint. U intersection v is empty, but u not equal to empty, v also not equal to empty. These properties are there. Okay, now because f is continuous functions and u is open set in fx, then the inverse image is also open, right? So the continuity of f implies, what implies f inverse u and f inverse v are open in X, right? So they open in X, and what does that mean? That means if you have something which is open in X, okay, yeah. So okay, and also what? So this is onto map, right? From X to F is onto map, right? And this is open in X. So thus, what do you have? You have X is actually union of F inverse U union F inverse of B, right? Okay. So note that here this F inverse of U intersections F inverse of V is empty, because if it is not empty, so that will be belongs to U union V, and that is a contradiction because union V is empty, right? And similarly they are open. Okay, so thus this becomes a separation of X, so X is disconnected, which is a contradiction, right? Connected, which is a contradiction, which is a contradiction. So what does that mean? That means that the continuous image cannot be disconnected under continuous functions. The continuous image of the connected space cannot be disconnected, it has to be connected. Okay, clear? So this is an important, very important theorem. In particular, you can say, so as a corollary you can say that homeomorphic homeomorphic spaces are a homeomorphic image of connected space is connected. Okay, connected space is connected, and because homeomorphisms are also continuous functions, right? So what does that mean? That means if you have connectedness, if you know that two spaces are homomorphic, and if you know that there is a connected space in one another, the image is not connected, or vice versa. If you have a connected space and the P image is not connected, then they two cannot be homomorphic. Okay, clear? So now the next question we want to know that what about the Cartesian product? Like if you start with the finite. Okay, so let me start with Cartesian product of two elements. So let the theorem. So okay, so the finite Cartesian product of connected space is connected. Okay, so we will do it for two, and then the mathematical induction we will prove for the rest, right? So so again the proof is elegant. So we start with let X and Y two connected space. Okay, B two connected space. Okay, so then how the X cross Y look like? So X cross Y. So let me just draw a picture. Say, suppose this is my x-axis, this is y-axis, and I need to prove that the whole plane, xy plane, is connected. Okay, if x is connected, y is connected, then the plane is connected. Okay, that is the meaning of Cartesian product. So what we can do, we can draw parallel lines here. So let me draw a parallel lines here, or maybe passing through a point. Say the point is say AB, whatever AB, yeah, you choose a point. And then you can also pass to this kind of vertical lines, right? These are never-ending lines. Okay. Now, if X is connected, then these vertical lines are also connected, right? Whatever line you draw parallel to X, because they are homeomorphic. Similarly for this. Okay. So let me just first take two lines. One is this line, which is we can denote by. Okay, so this is the point AB, which is inside the line, and this line you can denote by. So this is X is varying, Y is constant, right? So you can write down the X cross B. Okay, so this line, the line, or rather parallel line, parallel to x-axis, the line. So this is I read X cross B. So how you can write X cross B? X cross B is all the points of this from X cross comma B such that X belongs to X. Okay. So this is a line parallel to B is connected as it is homeomorphic, right? Homeomorphic to X, right? So it's homeomorphic to X, so it has to be connected because X is connected, right? Similarly, you see that line here. So I'm writing the line passing through. Okay, so this line you can think as a line which is passing through the point this, okay, so okay, 1 minute. So maybe I can write down differently. Instead of these, I can write down it is any points. Okay, so this is AB is inside the line XY, but I can choose any lines here. Doesn't matter, any line. Okay, maybe which is passing through some distance X. Okay, and so this will be these lines are parallel to this y-axis, so you can write down X cross Y of this one, right? So given any X, so you can write down these lines. So okay. Okay, again, so let me write down properly again. For any X belongs to X, the line X comma Y is connected as it is homeomorphic to Y, right? Okay, so if you choose one such lines, it doesn't matter, say for example these, and then the first line, then you have kind of this kind of plus sign, right? So the plus sign is connected or not, and so thus you take these plus signs as kind of tx which depend on X. This is collection, this is this first line X cross B union the second line which is small x cross Y, right? This is this line. Okay, whatever, doesn't matter. X depends, X can be anything. So these lines are connected because you have to connect a space, and you see that it has a common points. Okay, because the common point is X comma B. So this XB, this is both lines. So this is inside the line X cross B intersections X cross Y, right? And yesterday, or sorry, rather in last lecture, we proved that if you have union of connected space such that intersection is non-empty, then that union is also connected, right? So thus Tx is connected, right? Okay. Now when you vary x, then what happens? If you vary x, so what does that mean? So this line is fixed, remember, and then you are varying these vertical lines. If you are varying all the x, then it will cover the full plane. Okay. So what does that mean? That means the plane x cross y is nothing but union of Tx. Okay, x belongs to x. Is that okay? Because we are varying x and then it will cover everything, right? And we know that Tx are all connected for every x. Okay, again, so this is union of connected space. So now if I show that every Tx is a common point, then we are done, right? Now what is the common point that every Tx has? So that is nothing but the point that is the point of that original line on xb, right? Or in particular the point AB. Now see that as the point AB that belongs to the intersection of Tx. So we have union of Tx, which is nothing but the Cartesian product x belongs to x is connected. Okay, so that tells you that if you take the Cartesian product with two connected space, that has to be connected. But then you're done, because in general case, if you have n many connected space, so in general if x1, x2, xn are connected, then what happens? You just write down A is so this is mathematical inductions. Okay, I'm using that mathematical induction as it is true for n minus 1, right? So you can write down A1, x1, x2 cross xn minus 1 and b equal to xn, right? So if you use mathematical induction, you can show A is connected, B is connected, and again for the case when n equal to 2, you know that this is true. So A cross B is connected, which is nothing but the finite Cartesian product of x1 to xn, right? So finite Cartesian product of connected space is connected always. Okay, so so now then the question is that what about for if you know this is the true, then what about for the case when it has countably many or uncountably whatever, not finite, infinitely many product. Okay, in fact that we cannot say in general, we may connect or may not connect it. Okay, we will give example. But before that, let us just try to prove one more important thing, that R is connected. Okay, real number R is connected, and obviously, so we will start with the proof that if you start with any intervals, okay, any intervals of R, that is connected, and then obviously then that implies R is connected, because R is still the full interval, right? So what is our goal? Our goal is to the real number, so R is connected. So this is our goal. And so we'll start with some intervals. Okay, so it doesn't matter. So if you choose open intervals, then that contains a closed interval, obviously. And so let us start with closed interval, because whenever you have open interval, you can always choose a closed interval inside that. So let so you have a closed interval, say B, Z R, then this is connected. Okay, and so with the loss of generality, I'm assuming that it is, if it is open set also, that is true, because you can play the game with any 2 points on open set, because these are all open sets are nothing but something called convex set, right? So so you have a closed subset inside sitting there, and then you can play the same game. Okay, in fact, it is true for open arrays, closed array, everything. So with the loss of generality, I'm just assuming that you have this, so it is connected. How do you prove it? So obviously, so let first assume that it's not connected. So, or on the contrary, you can say that on the contrary, let on the contrary, what do you assume? That this is not connected. Okay, so what does that mean? That means you can have something U union V, okay, where U and V are open set inside this, right? So what does that mean? That means you use open set, use intersection of some open set. So so how do I write? Yeah, doesn't matter. Okay, so U and V are open disjoint non-empty subset of this interval. Okay, and U and V are obviously bounded to them. Okay, and then we will use the very nice property of R, which is called LUB property, right? Whenever you have bounded subset, it has LUB by GLB. So you will use this property. So let the supremum, say S is the supremum of say U. Okay, suppose S is the supremum of U, and see, my assumption says that A less than B, right? Because I choose the interval A plus B, right? Now suppose if you have a supremum always exists, right? If S is the supremum of U, then what happened? Then where is S? The question is that whether S is inside U or S is inside V. This is the question. Now, if S is inside U, then okay. First, let us prove that what happens if S is inside V. If S is inside V, so claim. So there are two cases now. Just let me write down case 1, case 2. So if S is inside V, that I don't know, I'm assuming, then is an interior point of V, because V is open set, right? It's an interior point of V. Thus you have an open set. So there is open interval containing S, which is totally inside V, right? So thus so you will have something, say S minus epsilon, some epsilon to S plus epsilon, that is completely inside V. Okay, so what does that mean? That means there are points which are also upper bounds of element of U, right? See, what I am assuming that S is inside V. So S is inside V means I am assuming that okay. So there are two things can happen. S can be equal to B also, or S can be in between, less than B also. But in any case, you will have this kind of issue, right? But then what happens? Then it will violate the supremum property, LUB property of that, right? Why? Because that x plus s minus epsilon by 2, this is the element of that V, and So this is also less than okay, so no, I should not say that. So S minus epsilon plus, okay, plus I should say. No, let me write down properly. So I have S minus epsilon and S. So how do I write down? So S plus epsilon, S minus epsilon by 2, not plus. S minus epsilon by 2, yeah. So this is an element of that interval, obviously, and you see this interval is inside V, so this is inside V, and also this is S minus epsilon by 2 is also an upper bound, right? This is less than, obviously less than S, and S minus epsilon by 2 is also an upper bound of U, right? But this is a contradiction because this is the least upper bound, supremum, right? So which is a contradiction? Is a contradiction as S is the supremum of U, right? So what does that mean? That means S cannot be inside V. Okay, so then what is the option? So it has to be inside U. Now if S is inside U, then what happens? Then again there are two cases. Either it has to be equal to A, or it is something which is in between A and B. Okay, but again you have a open intervals. So again, so similarly, case 2, if S is inside U, then again as U is open, so you will have some interval, right? S minus epsilon to S plus epsilon, or rather epsilon dash. You may feel the same epsilon. No, it can be some different epsilon. This is totally inside U, right? And again you see that S plus epsilon dash by 2 is that is bigger than S, and this is an element of U, so S cannot be upper bound, right? So this is bigger than S, and S plus epsilon dash by 2 is element of U, so S cannot be a supremum or the supremum, right? Because you have element bigger than the upper bound, okay? Not a supremum, okay? So this is the technique, and the most important property which we are using here is that every bounded subset of real number is having this LUV property, okay, LUV GLV property. And if it is ray, then also it is possible, then at least either it has a LUV or a GLV, right? Open rays or closed rays, okay? So whatever is happening, it may be upper bound or lower bound, and then you can get a conclusion from that. So what does that mean? So that means every open interval, so every intervals of R is connected, and hence R is also itself connected, right? So this is the proof. In fact, this proves a more general theorem that tells you that not only R, if you have a ordered space with ordered topology with some property called linear continuum, then it has the same property. This must be connected. So let me define it. So what do you mean by linear continuum? Then you'll understand. So here is simply order set X having at least 2 points points is called a linear continuum if we satisfy this property. What are the property? First, that X has the LUV property, least upper bound, and number 2 is what? That if you choose two elements from X, then there exists another element, something say Z belongs to X, such that it is inside that, it is in between this. Then we call this set X with that order of topology is linear continuum, right? And the way we prove it, it is showing that it is true for any linear continuum because we only use the ordered method, nothing else, right? So corollary of what we have done, or rather prove that every linear continuum, okay, every linear continuum is connected. Okay, so this is not only special about R. Whenever you have a linear continuum, it must be connected. Okay, so with the help of this, we can now prove that it is not always true that if you have a connected subspace, then the infinite product is connected. It may be or may not be. It depends on the topology. So the connectedness is completely topological property because it depends on the open set, right? And the separations of open sets. And the question what we can ask again here, that whether infinite product as a question. So is infinite Cartesian product of connected space is connected? This is very natural question, and the answer is no. It may or may not be. It depends on the underlying topology. Okay, so maybe first I will give you examples where it is maybe not connected and then connected, or some vice versa, whatever. Okay, so so I will first give an example where it is connected. So here is the example. So what we'll do, so you have X, which is R omega or R in whatever, this is the same, okay, with product topology, okay. We will show that X is connected because R is connected, X is connected. I will show here. Okay, so here what you will do, you will start with a proper say subspace. Let me write down this until the n, so the subspace of R capital N. What is this? So this is a collection of all the sequences of these forms. So x1, x2, xn, and this 0, 0, 0. After in that point everything is 0. Before that it may be 0, may not be 0. Okay. Now obviously this will form a subspace of Rn, right? And you can also show that this is homeomorphic to Rn, that Cartesian product of real numbers n times, right? So these subspaces are homeomorphic to Rn, and Rn is also connected. We just proved that finite Cartesian product is connected. So this Rn tilde n are connected for each n, right? Now what we will do, so we will define this symbol R infinity, which is union of this R tilde n belongs to natural number. Okay, so this is also a subspace of Rn, obviously. Okay, and can you say R infinity is connected? Yes, because you see that all those unions of the connected space, and it has a common points. So R infinity is also connected as what happened as you have count point 0 0 0 0. So this is inside intersection of, right, for everything. So this is a count point, and if you have union, arbitrary union of context connected, if you have a count point, right? So R infinity is connected, and now R infinity is connected subspace of Rn. Now how do I prove Rn connected? If I prove that Rn is the closure of R infinity, I am done, right? The closure of connected space is connected. So this is my claim. Now the claim is that is R infinity closure is Rn. Okay, so what does that mean? That means every point of Rn is a limit point of R infinity, right? So let me start with that. So let, if you choose a point, say x1, x2, dot 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 something belongs to R infinity. Okay, and so we need to prove this is a limit point of R infinity, means whenever you choose a open balls containing x, they will intersect R infinity, right? So let so you have open ball, basic open balls of this form, u1, u2, and so on. So maybe let me write down that some n naught position, after that everything is R. Okay, because it's a product topology, right? So be a basic open set containing x. That is what? That is these xi's are inside ui's. Okay. Then I need to show that this u intersect with R infinity. So how to show that u intersects with R infinity? So if you show that there exists a common point that it belongs to both u and infinity, that R infinity, then you are done, right? So now you see that you can write down a point, say maybe write down y dash, sorry, x dash, and x dash is what? X dash is the point of the form x1, x2, and dot dot xn, and then 0 0 0 0. Okay, clear? Now this is obviously this is a point inside R infinity, because R infinity is union of all those whose coordinates are non-zero up to finitely many places, right? After that everything is 0, so this is in R infinity, and this is also inside U. Okay, so this is inside R infinity intersections U also, because x is an element of ui and 0 is an element of R, right? So U intersection R infinity not equal to phi, and hence that is the limit point, right? X belongs to limit point of this, or rather R closure, right? And now, so what does that mean? That means every element of Rn is element of R closure, and converse is obviously true. So what does that mean? That means this has to be equal to Rn. Okay. So what does we prove? We just prove that if you have product topology on R, then this R infinity under product topology is also connected. In fact, it is true for product topology of any arbitrary space. Instead of countable many, you can go for uncountable many. Still, this is true. Okay, so another example I will show that what happen if it is not this topology. Okay, so for example, you have another topology in R infinity, is called box topology, and what happened, and then we will show that this with box topology. Okay, topology is not connected. Okay, so with product topology is connected, but box topology is not connected. So what does that mean? That means the connectedness is a topological property that depends on topology, right? So how do you prove? So okay, so you can write down this R infinity with box topology into union of say A union B, where A is a subspace. What kind of subspace is that? So A is the set of the bounded sequences. S is the subset of bounded sequences. See, Rn is the elements which are kind of a sequence, right? So bounded sequence means that after if there exists a natural number n such that all the elements of the set are inside that. So bounded sequences are those sequences which is bounded by some real number, right? And B is unbounded. B is the subset of unbounded sequences. Okay, now you show that these two are actually disjoint, then you are done. If you show that these two are disjoint, so both are open obviously, and obviously, sorry, these two are disjoint is obvious because a sequence cannot be both bounded and unbounded. If I show that both are open, I am done, right? And both are open, that is also easy. So that means every point of these are interior points, right? So you choose that you choose a sequence, so x, which is x1, x2, dot inside A. Okay, B, a bounded sequence, and then we will show that there exists. So this is interior point of A means what? There exists an interval which totally contained inside A. Then you are done, right? And that's obvious. Then you choose the interval U of this form, say x minus anything, say half to x1 plus half, then cross x2 minus half to x2 plus half, and so on, cross dot. So this is I am choosing interval length 1, right? And hence the intervals are also bounded, right? Now see that this is a basic open set containing x, and it is also totally inside A, because every element, if you choose any element, it has to be bounded because x1, x2, xn is bounded. So you cannot go beyond minus half to plus half. So what does that mean? That means every point of bounded sequence is actually an interior point, right? And similarly, every point of unbounded sequence space or unbounded sequence is also interior points, because if a point is unbounded, so what does that mean? That means you cannot, so either does not exist an integer or real number n, that every point is less than equal to that, right? More of that less than equal to that. And hence what happens? Hence you cannot find out you can find out a sequence of intervals which contains that points and which is unbounded, and this is the similar proof, right? So similarly B is also open. Okay, so what does that mean? That means A union B is you can write down this, and A intersection B, this is empty, and obviously they cannot be empty itself. A and B, they are not empty because you have sequence, right? You have 1 1 1 inside A, 1 2 3 4 5 6, this is inside B, right? They are not empty, and most of them they are also open. Okay, so what does that mean? That means Rn is disconnected. They will form a separation. So we just proved that the box topology, Rn unit box topology cannot be a connected space, right? So this is a simple observation, that if we have box topology, and if we have instead of R, if we used to choose any connected space, then this kind of countable infinite product, Cartesian product, this cannot be a connected space. Okay, and we will finish this today's lecture with a very important theorems. That is, you can say that you have already learned intermediate value property of real numbers, and this is also true for arbitrary topological space and continuous functions. So let me define what is that. So we can write down this intermediate value theorem. Okay, and what is the statement? The statement is that, so suppose you have a continuous functions from say x to y is continuous, and x is connected, y is order set. So y is order set means it has order topology. So y has order topology. Okay, and then okay, this is given. So if you choose say 2 points, say A, B belongs to X, such that there exists R belongs to Y in between f of A and f of B, then what happens? Then there exists a C belongs to X, or rather you can say the in between A or B. So I don't care, I did X here, so I don't, so I will tell you for real line, this is the portion you have learned belongs to X, such that f of C is equal to R. Okay, so in real line you replace your X by the intervals, any closed interval AB, okay, which will be connected, and Y by R, then they map from closed interval AB to R, and R is also topological space with order topology, right? So what does that mean? That whenever you have a point inside the image of that, so the pre-image is also, it belongs to inside that AB, right? So it's kind of continuous image of the intervals in intervals. Okay, close intervals, okay, intermediate property, and the proof is also not so difficult. So see, anyway, in any case, what you can write down, that f of x, which is a image of x under f. So this is a subset of your y, right? So you can write down, because y has order topology, so you have open race. So you can talk about two set. One is fx intersections minus infinity to r is inside y, and b is f of x intersection r to infinity, right? So they are open set in y with respect to order topology, because this is open, and then obviously if fx is open inside as a subspace topology, so this is open in I should say f of x, not y. With respect to subspace topology, a and b are open, right? So now if A and B are open, and you see that they are non-empty, because f of A is inside A and f of B is inside B, okay, because R is in between f of A and f of B. So f of A is less than R, f of B greater than R, okay. So now if suppose there does not exist any R, then what happens if there does not any C, if there does not exist any C such that f of C equal to R, and then what happens? Then A intersection B will be phi, okay. And if A intersection B will be phi, then what? Then f of x is disconnected, right? Because you can have separation of f of x, right? But this is a contradiction, because x is connected and y is continuous. So continuous of the connected space is connected. So which is a contradiction as x is connected and f is continuous, right? Continuous image of connected space connected. So what does that mean? That means you must have an element C which satisfy the condition f of C equal to R, okay. Is that fine? Otherwise that too will define a separation. Okay, so I will stop my lecture here today.